Here we're going to write the energy balance for a stirred tank reactor. So general unsteady state stirred tanks, such as, for example, startup of a Cstr. For a simple reaction, A goes to B. We'll assume the work term is not important, and we're going to make our reference temperature the reactor temperature. Notation, molar flow rate of A, moles per time coming in, and let's in general assume some B is coming in, and the feed temperature T0. Temperature leaving, molar flow rate of A, of course, should be different if we have reaction, likewise for B, and then the concentrations of A and B leaving the reactor. Now inside the reactor, temperature is the same as leaving. Concentration of A, concentration of B is the same as leaving. And then N sub A is the number of moles of A in the reactor. N sub B is the number of moles of B in the reactor. So if I now write the energy balance, I'm going to look at an accumulation term. So in the reactor, number of moles of A times the heat capacity of A plus the number of moles of B, heat capacity of B. And of course, number of moles of A and B are going to change with time if it's an unsteady state Cstr, and the derivative temperature with respect to time. Now, I picked the reference temperature to be the reactor temperature, so I'm going to have a flow term for energy in for A and for B, so molar flow rate times heat capacities, feed temperature minus inlet temperature. There's no flow term for energy out because we're leaving at TR as our reference temperature. And then we have a heat reaction term, which is evaluated at our reference temperature times rate of reaction times volume, and then in general we have heat transfer. So let's look at this heat reaction term. So heat reaction, evaluated temperature T, and then first order reaction that we're assuming we have something that looks like this. So let's just see if this makes sense in terms of how the temperature should change. If the first term on the right, if the feed temperature, let's say we have an exothermic reaction, and so the feed temperature is less than reactor temperature. Let's say it's even adiabatic. We expect that this first term would be negative because feeding in a cold feed would tend to lower the temperature. And then the second term, well, exothermic, this is negative, this term is negative, so the two terms together, multiplied together, are positive. The heat reaction would tend to raise the temperature in the reactor. And of course, if we had heat transfer, it would be negative if removing energy from the system. Well, we can also look at what's this equation look like if it were a batch reactor. And let me just pause and write that down. So for a batch reactor, this circle term goes to 0. Change in temperature is related to heat of reaction and our heat transfer. Let's look now at a steady state Cstr. For a steady state Cstr, the accumulation term is gone, and we have the flow term in, no flow term out because we picked as our reference temperature the reactor temperature. And then we have the heat transfer term. And a semi-batch, of course, looks just like our unsteady state Cstr, depending on which terms we can ignore. And that depends on how the system is set up. And we solve these energy balances simultaneously with mass balances to determine the reactor behavior.